Katya, for that warm, oops, all right. Well, thank you, Katya, for that warm welcome, and thank you for inviting me to give this talk. So today I'm going to talk a little bit about determining a Riemannian metric from least area data. And the results and work that I'll present today is joint with Spiros Alexakis and Adrian Nachman, both at the University of Toronto. All right, so here's my plan for the talk today. So first, to just provide some historical context for the problem that we'll be looking at. And the particular problem that we're going to be looking at, you can view as a lower codimensional rigidity problem. So I'll introduce what I mean by that. Then I'll discuss a sketch of one of the global results that we've shown. And if I have some time, I'll discuss some future projects. All right, so first, let's look at the historical context. So as many of you know, there's a very classical geometric question called the boundary rigidity problem. And it basically states that if you have a Riemannian manifold with boundary, and let's say you know the geodesic distance between any 2 points on the boundary, can you use this information to recover the Riemannian metric? And if it's the case, then you would say, well, the manifold is going to be boundary rigid. So what are some obvious obstructions to this problem? So one, boundary fixing diffeomorphisms. Of course, if I don't change the boundary, but I change the inside, then I can only recover the metric up to this coordinate change. Another obstruction is if I have a very large region of positive curvature, then if I look at the distance between any 2 points on the boundary of my manifold, there is no geodesic that's minimizing length that's ever going to go through that very large mountain of curvature. And so I'll never know what the metric is going to be here. So what do you do at this point? So what you can do is say, rule out these classes of manifolds. And if you do that and say, well, I don't have any conjugate points, then you call this manifold simple. Or you can give yourself different data, say the lens data, where you force yourself to not be a length minimizing geodesic, but just any geodesic, and you point yourself in the direction of the mountain, let's say, then can you do something? So in 1981, Michel conjectured, well, perhaps all simple manifolds are boundary rigid. So very briefly, let me just look at some selected results on this problem thus far. So early on, some very special cases were shown by Michel, Bromov, and Krook. In 2003, Lasses, Sharfutinov, and Ullman showed, well, if I have a metric that's CK close to Euclidean, then these manifolds are boundary rigid. I can identify the metric from this distance data on the boundary. In 2005, Stefanov and Ullman showed, well, if I have two metrics that are both simple, and I know that one of the metrics is CK close to the other, well, then I can use this information plus the knowledge of distances between any 2 points on the boundary to show that the manifold is boundary rigid. In 2005, Pestov and Ullman showed that the simple two manifolds are boundary rigid, which kind of sealed the deal for the two-dimensional case. And I'll discuss a little bit more about this result in a moment. Much later in 2010, and then in a later paper in 2013, Barago and Ivanov showed, well, let's say I have a metric which is simple, and it's either going to be C2 close to Euclidean, that was their 2010 paper, or it's C3 close to a hyperbolic metric, that was their 2013 paper. Then in this case, these manifolds are going to be boundary rigid. I can identify the metric from this boundary distance data. Much more recently, Guillermo, Graham, Stefanov, and Ullman showed that if I'm in an asymptotically hyperbolic setting, what I can do is look at the distance between 2 points on the boundary at infinity and look at the renormalized length of these geodesics. Using this information, they were able to also reconstruct or recover the metric uniquely. And very recently, Stefanov, Ullman, and Baji showed that if I look at a manifold that indeed has this kind of convex foliation condition, so here's my manifold, and I can foliate it out by convex submanifolds. This plus this lens data, where I have the lengths of any geodesics plus the direction in which I point, this information, you can use this to then uniquely recover the Riemannian metric. So let me move on and just highlight this result of Pestov and Ullman, as it's going to relate to what I'm going to discuss in a moment. So in this 2D rigidity case, again, I'm looking at a manifold which is two-dimensional and simple. And what Pestov and Ullman showed is that knowledge of the boundary distances is equivalent to knowledge of the Dirichlet-Neumann map for a conductivity type problem. And the conductivity type problem that they looked at was the Laplacian on the manifold. So in 2001, a little bit earlier, Lassus and Ullman showed that if I look at the Laplacian on a manifold, I'm looking at harmonic functions, and I give some boundary data, then the Dirichlet-Neumann map for this problem uniquely determines the metric. And here in this Dirichlet-Neumann map, what I'm taking is the function that's on the boundary, and I'm sending that to the normal derivative, basically, of the interior potential. Here, nu is the outward pointing unit normal vector to the boundary then. So this Dirichlet-Neumann map allows you to uniquely identify the metric. So by connecting distances to the knowledge of this Dirichlet-Neumann map, Pestov and Ullman were able to settle this two-dimensional simple manifold case. As it also relates to the problem that I'm going to discuss in a moment, let me just talk a little bit more about conductivity type problems in 2 dimensions. So Adrian showed that if I'm looking at this anisotropic case of Calderon's problem, I can take the conductivity and write it in terms of the metric and look at this particular type of conductivity, pardon me. Then looking at this conductivity problem, Calderon's problem, in fact, this transforms into just looking at harmonic functions on the manifold. And if you then introduce isothermal coordinates on this 2-dimensional manifold, you can reduce to the isotropic case of Calderon's problem, which just means instead of having a metric defined conductivity, now I have a function. So in that isotropic case, what Adrian did is he made a little transformation, if I'm looking at smooth enough conductivities, and showed that this conductivity problem then transforms into a Schrodinger equation on the manifold. And then what he did is then reconstructed this potential for the Schrodinger equation from the Dirichlet-Neumann map for smooth enough conductivities in this case. And this problem is going to come up a little bit later on in what I'm going to discuss when we're looking at area data instead of the data of giving links between any two geodesics, points on the boundary. I should also mention that the best result in the 2-dimensional case was shown by Astela and Pivarenta. And they did this for actually just measurable conductivities on the 2-dimensional manifold. All right, so now let me introduce to you what I mean by a lower codimensional rigidity problem. So what I aim to ask is, can we determine a metric from area data? So here, instead of looking at distances and geodesics, I can think of a geodesic as a dimensional 1 submanifold in my larger manifold. And so its codimension is going to be n-1. But instead, let's say I'm looking at an area that sweeps through the manifold, and I'm looking at the area of a surface. And a surface is going to have 2 dimensions, and so I'm looking at a codimension n-2 version of boundary rigidity. And here, instead of considering, as I said, geodesics between any 2 points on the boundary of my manifold, let's instead look at a manifold and say I take a curve on the boundary and sweep out by some surface. So indeed, here's the question that I now pose. Let's consider a Riemannian manifold, which I'm denoting by M, and its Riemannian metric G, and it has boundary, partial M. Then for any simple closed curve gamma that sits on this boundary of the manifold, let's say I give myself the data that I know the area of any least area surface that I can fill in this curve with. Then can I use this information for any such curve I know any of these areas? Can I use this information to recover the Riemannian metric? And this is what I mean by a lower codimensional rigidity problem. So today, what I'm going to say is the answer is yes, under certain geometric conditions. And in some cases, we're not going to use all of the curves that we could possibly put on the boundary, but just a subclass for a much smaller family of curves. There's a very interesting connection of this lower codimensional boundary rigidity problem to physics, in particular into arising in the study of anti-de Sitter and conformal field theories. So this is what I mean by ADS-CFT, ADS standing for anti-de Sitter, CFT standing for conformal field theory. And so this ADS-CFT correspondence basically states very, very broadly that it relates quantum gravity as it's defined in some asymptotically anti-de Sitter spacetime to a conformal field theory that's defined on the boundary of this manifold. And there's lots of conjectures within this theory, but one that I'm going to highlight for you today is the Hibeni-Ryu-Takanayagi conjecture. And what it basically states is there's this quantity called the entanglement entropy of some region in this manifold, let's denote it by A, in this conformal field theory, and this is into a one-to-one correspondence with the area of a least area surface that's kind of like suction cupped onto the boundary of this manifold, or pardon me, this submanifold. So in pictures, what do I mean by this? So let's say this big, huge block here is my anti-de Sitter space, and this square here I'm denoting by the boundary. I have some submanifold on the boundary, let's say A, and I know the entanglement entropy of this region. That number, whatever it is proportional to, let me take a least area minimal surface. Here I'm greatly exaggerating, let's say Y, and it shares the same boundary as this region A. This area then defines whatever this quantum entanglement entropy is for this region A. So in this ADS-CFT correspondence, what physicists often expect is that knowledge of what these conformal field theory objects on the boundary, they should be able to provide information for the bulk metric. And in fact, you expect knowledge would then of components that are arising on the boundary would determine the metric in the bulk. And so the big question is this true? And even if it's not true in its full generality, just what features of the bulk can you identify given some kind of information on the boundary? So these are two major questions that they're looking at. And in the regime and in our result that I'm going to present to you today, there have been some some work in the physics literature that's built on our results. So one in particular looks at taking this area data in Riemannian manifolds of dimension 4 or greater and filling in by least area surfaces that have topology of a disk. And they use this information to then recover the Riemannian metric and indeed then a Lorentzian metric by a certain Wick transformation from this information. And then later on, they extended this work. Instead of looking at minimal surfaces which have the topology of a disk, they looked at minimal surfaces which have higher genus, so say like a torus or tori or something like this. And again, in dimensions greater than or equal to 4, we're able to use this information to argue that they can uniquely recover the metric in this case. All right, so what is the result that of ours that they built upon? So it's the following, and what we can actually do is we can recover a Riemannian metric from knowledge of the least areas of minimal surfaces for 3 classes of manifolds. And very briefly, the first 2 classes that I'm going to introduce arise from the following trade-off of information. So the first is the less area data that I want to give myself. So I'm going to give myself area data for a small family of curves on the boundary. But if I do that and I have this less data, then I'm going to have a trade-off of I'm going to have more restrictions on the geometry, which we'll see in a moment. And this is for the first 2 classes. The final and third class in this case arises from the alternative trade-off where I give myself lots of data, so more data available, and then I'm allowed to put fewer restrictions on the metric. And today I'm going to introduce all three of these classes, but I'll discuss the result just for the first two classes, as kind of the rest are built upon the strategy presented in this result. So what is our global result? So what we're able to show is that if I have a Riemannian manifold, which is of this class 1 or class 2, putting off the kind of description for just a moment, let's say I know the metric on the boundary, and suppose for any family of simple closed curves on the boundary, which I'm going to denote this family parameter with a t, and any nearby perturbations of this curve. So I'm allowed to wiggle it a little bit. For this two-parameter family of curves, I know the area of any properly embedded surface, that is a surface whose boundary is indeed this curve, and the surface with boundary curve, say gamma st, I'm just going to denote by a capital Y st. This surface solves the least area problem for the boundary data of gamma st. And I know the areas of these surfaces. Then the metric is uniquely determined up to diffeomorphisms which fix the boundary. So what is the setup in this case? Let me explain this class 1 and class 2 in a bit more detail. So here I have some Riemannian manifold, which I'm still denoting by mg. Gamma of t is one particular curve I'm going to give myself on the boundary, and I'm allowed to fill this in by a minimal surface which has least area, and I'm calling that y of t. And the class of curves that I have is not just one of these, but in fact a whole foliation of curves. And they're filled in surfaces. With no gaps. So an entire foliation all the way through the manifold by these kind of slices of least area surfaces yt. So that's the initial setup. My manifold comes with this information and this structure. Now let me make the distinction between first and second classes. So let me also additionally assume that just for technical reasons, my manifold is at least C4 smooth. I'm going to work in 3 dimensions, and why 3 dimensions I'll highlight as we go through the proof. I'm also going to assume, just to make my life easy so that I can solve Plateau's problem for any curve that I do give myself on the boundary, I'm going to assume that the manifold has strictly mean convex boundary, partial m. And as I kind of drew in the picture, I also assume that I have a foliation of the boundary by these simple closed curves. Recall I was calling these things gamma t. Oh, I actually even put that here, wonderful. And then for this foliation of curves that I have on the boundary, this moreover induces a foliation of the manifold itself by area minimizing disks. So all of these surfaces which have topology of the disk. And I'm calling these surfaces again with a capital Y of t. All right. So here's the distinction for class 1. I have all of this structure that I introduced in the first 2 slides. And additionally, when I zoom into the level of curvature, my metric basically looks flat. So how much zooming in do I want to do? Well, I'm going to look so that my metric is at least C3 close to the Euclidean metric. So looking pretty flat, even all the way up to the level of curvature. My second class arises from a trade-off between having more curvature, but then I want to make the manifolds a little bit skinny. So I'm going to call this class of manifolds straight thin. And so what this means is that if my manifold in the direction of the foliation by the curves is fairly straight, then I'm allowed to take minimal surfaces which have a wide girth, so this area could be large. But if my manifold is, say, fairly curvy or has some high curvature in the direction that I'm foliating the manifold by, then I want my minimal surfaces to have area that's relatively small, so small girth in this case. And this is the trade-off. Straighter in the foliation direction, allowed to have a larger minimal surface, more curved, in the direction in which I foliate, then I want these manifolds to look fairly skinny. And so the minimal surfaces are going to have small area. All right, so that's class 2, straight thin, class 1, close to Euclidean. So before I present the proof of this result, let me just ask another question, which is, what if we only know this kind of area data in some region near a point on the boundary? So let's say I have this area U, and for any foliation I give myself of this neighborhood U near P, I know can fill in by least area surfaces, and I know the areas of these surfaces. Could I then determine the metric in a nearby point, let's say somewhere in this region B? And the answer is yes, for a very simple reason, that these kind of neighborhood, let me backtrack a little bit, this neighborhood V, you can think of as a thin, straight thin manifold. So from this, we have a little local result. And again, I'm looking at Riemannian manifolds with our 3-dimensional and with boundary. Again, I'll assume that the manifold is at least C4 smooth near this point P that I've picked. And I have this neighborhood U on the boundary of the manifold for which I can foliate by these simple closed curves. And moreover, for this family of simple closed curves and any nearby perturbations of them, I can fill them in by a least area surface, and I know the areas of all these surfaces. So from this information, then we can uniquely determine the Riemannian metric in some neighborhood of the bulk manifold of this point P. So that's the local result that we can get right away. So in the remaining time, let me now sketch the proof of the first global result. So either looking at manifolds of class 1, this close to Euclidean condition, or manifolds of class 2, where I have this straight thin trade-off. Let me show you how we then can uniquely determine the Riemannian metric in these cases. Whoops. All right. So first, let me give you a kind of bird's eye overview of the proof. What do we want to show? So we want to show that for the least area data for this foliation of surfaces of the manifold, which I'm calling again by YT, this and its nearby perturbations, all of these areas knowledge of all of these areas allows me to uniquely determine the Riemannian metric. And what we're going to do in the following argument is solve for the metric on, say, one of these surfaces, and then move along the foliation from surface to surface to surface. Key to this is we'll use the fact that we're working with 2-dimensional surfaces and use the conformal structure now of the surface to write the metric in a convenient way. So in such a way as this, where now here phi that I've denoted here is the conformal factor, say, on one of these surfaces on, say, some YT. And then I have some off-diagonal components. What I mean to highlight here is now when I've written the metric in this kind of convenient way, I'm going to be solving for 4 functions, essentially. The off-diagonal components and the diagonal one and this conformal factor on each of these surfaces. So I'm looking for 4 functions. Now, it might seem a little bit strange to try and identify the conformal factor on a surface because you can put whatever conformal factor you want. Or pardon me, many conformal factors, I should say, that's the correct thing. However, you can impose uniqueness by extending the manifold to be asymptotically flat and imposing then a condition at infinity of what the conformal factor should look like. So I then have a hope of indeed trying to locate these 4 functions. All right, so more of the main proof ideas. So the big key here is I'm going to use this foliation to relate geometric data, this knowledge of all of these areas, to data for a partial differential equation on the surfaces. So how do I do that? Well, what I can do is I can look at, say, one particular surface. Let's just pick on y0. And I can use the foliation to kind of write a normal variation of y0 up to the surface yt. And then compute, well, what's the second derivative of area in this case? And when I do so, what I end up identifying here is this quantity to the right. And here, what sits in this component is called the stability operator on the manifold and on this particular surface, in fact, and then some boundary data information. Here, V is just the normal, let me backtrack. N is the normal vector field on this surface, y0. B is telling me how much I push up, so it's scaling this normal vector field. And nu here is the unit to normal to the boundary of the minimal surface y0. So normal to the boundary of the manifold, but tangent to the surface itself. All right, whoops. So now in this coordinate system that I've imposed, what we see from taking the second variation in area from these boundary data, boundary components, is I actually learn the Dirichlet-Neumann map for the stability operator that sits on the surface. And instead of writing this in terms of the metric on the surface, I can use this conformal coordinates to actually write this in terms of a Schrodinger equation, which sits on the disk. Here I'm denoting a disk by D. All right, so from what I showed earlier, we know that the result of Adrian's allows us to take this Dirichlet-Neumann map data and determine this potential on this now one of my minimal surfaces. Now, since I know this potential, what you might think of as, well, this potential contains a bunch of curvature terms, maybe I can identify parts of the curvature. So that's one approach. A second thing to note is that since I know this function, instead of looking at the inverse problem, I can now look at the forward problem and solve for any boundary data that I give myself. So in particular, I can identify then any solution to this problem. And this is actually what we're going to use in what follows. Okay, so great. Now I know the Dirichlet-Neumann map for the stability operator on any of my minimal surfaces. And from that, I can solve for any push off, if you want, from the minimal surface. So this push off is sometimes called the lapse function. And it's a solution to this equation. So if I'm looking at my original foliation, let's say here's one of the surfaces yt1 and yt2, I know what this push off is. And I've identified this function. This corresponds to actually one of the metric components in the transverse directions to the surfaces. How do I figure out the other components now? Well, what I can do is use this variational data that I've given myself to wiggle the surface a little bit, although I've greatly exaggerated it in this drawing. So I take, say, one of my surfaces, which I'm denoting by yt, I perturb it a little bit and get a new minimal surface, calling it ys of t. And I had an original lapse function, which told me how much I pushed off the surface through the foliation. And now I get a new foliation of surfaces and a new lapse function, which tells me how fast I'm moving through that foliation. And from Adrian's result, I can identify each of these functions for all of the perturbations that I'm doing. All right, so now a lot of hard work begins. I now know all of these kind of lapse functions. Now I want to use this to get equations for my metric components and hope to solve. So what are these next steps? So now I know all of these lapse functions, and I'm going to linearize them in this perturbation parameter S. And when I do so, I get a very intimidating looking system of nonlinear and non-local equations, each in the components of the inverse metric is how it appears. All right, so in fact, it's nonlinear and non-local in all of the things that I'm trying to aim to solve. Fine, but here I get two equations from doing, say, two perturbations. So let me look at the regime that I did before. I have my minimal surface that sits here, let's say y of t, and I can tilt it in one direction and get an equation for one direction of the components. And I can do the same thing again. Here's still my minimal surface, yt. And let me tilt it in a different direction. I may be drawing this not quite well, but let's do it this way. And get a new lapse function. And this now gives me two equations for two of the metric components that I don't know. So remember, one of them I know immediately because I can identify what is this lapse function. And now I need to figure out two more of the metric components. So I can do two different tilts and get two of these equations and linearize them and get two other equations for the other components. And I'm left now to figure out an equation that helps me solve for that conformal factor on each of the surfaces. And to do that, I can get an evolution equation actually for this conformal factor by just realizing that I'm working with minimal surfaces, and thus their mean curvature is going to vanish, and that itself is an equation in the conformal factor. Okay, so now I have this big system of intimidating looking equations for the three other components of the metric that I'm trying to find. How do I find these components? So what we're going to do next is show uniqueness for this system by considering two different metrics now on my manifold, for which I have the same area data. That is, if I'm looking at my manifold, metric 1, and here's a curve on the boundary, say gamma, and I know the area of this surface. And now I look at the same manifold, M, with metric 2, I have the same curve on the boundary gamma, but maybe now I have some other minimal surface that fills this in. The area of this one is equal to the area of this surface for all of these entire foliation of curves that I gave myself as data. So that's what I mean by they have the same area data. All right, so now let's tackle this uniqueness problem. Oops, sorry, my fingers are not cooperating with me today. Okay, so if I now linearize these equations and take the difference now, I have two sets of equations, one for metric number 1 and one for metric number 2, and I take the differences, what do I get? So from the first equation where I just know what the lapse function is, I can immediately identify two of the components. So great, one of the components for each of the metric. So that's fantastic. So now I have two of the components of the metric remaining to show uniqueness for, plus the conformal factor. So now I look at those linearized lapse function equations. And what I get is a system that looks like this for these two things, where I have a change in the coordinates factor that appears. And this is the nonlinear, non-local part. But now that I've taken the difference, I've linearized it at the very least, but it still remains non-local. And then I take the difference of the equations for each of these minimal surfaces has 0 mean curvature. And that gives me an equation in terms of the difference of the conformal factors now on each of these minimal surfaces, one in metric 1 and one in metric number 2. Okay, so now I'm left with, instead of solving for 4 functions, I'm now solving for 3 functions, 2 of which are the difference of the metric components, and one is which is the difference for the conformal factors on the surfaces. And as I mentioned earlier, this kind of delta x term that appears here is the difference in the conformal coordinates on each of these surfaces. And this happens to be a pseudo-differential operator, which is unfortunately acting on all the things that I'd like to solve for. So what do we do next? Okay, so using this intimidating set of equations, what we show next is that for two of the functions that I'm trying to find, these differences in the metric components, we show that these are pseudo-differential operators, which now just act on the difference of the conformal factor and on the transverse derivative, so the derivative that's normal to the surfaces of the conformal difference of the conformal factors. And here's where I now use the conditions of either being C3 close to Euclidean or having this straight thin trade-off, is to do this inversion. To invert this system and show that it is indeed these two functions can be written as pseudo-differential operators on these two functions. Then the equation for the difference of the conformal factor, remember it was given by mean curvature vanishing on each of the surfaces. This can be written as a hyperbolic Cauchy problem as follows, where this term here, P, is an order 1 pseudo-differential operator in the tangential directions to the surface. All right, so then uniqueness to this Cauchy problem is then what gives us uniqueness of the metric components. Uniqueness of the Cauchy problem tells me that the conformal factors are unique. And once I know that, since I've written the other two functions as pseudo-differential operators acting on this difference, which is now 0, then those indeed are also going to be 0. So in this way, uniqueness for this Cauchy problem is what allows us to determine these remaining metric components. All right, so that finishes the proof of the global result for when I have the first two classes of manifolds, either being C3 close to Euclidean or having this straight thin trade-off. Let me briefly discuss what is the third class of manifolds that we can consider when, instead of just giving myself the data of having this one foliation and its of curves on the boundary and all of its nearby perturbations, where instead I give myself more curves on the boundary and the areas of the minimal surfaces that fill in all of these curves. So in this setting, the class 3 that we're going to look at, I'm going to call is a manifold which admits foliations from all directions. And it has two features. One is that I have my mean convex boundary, and what I can do is foliate this manifold by mean convex submanifolds, let's say NR. So I have this kind of onion-like structure to the manifold. Moreover, what's the data that I give myself? So let's say I have any point P that sits on one of these convex submanifolds. I can obtain a sweep out by area minimizing minimal surfaces up to the point P. So I have a bunch of curves that are on the boundary, fill in by all of these minimal surfaces that sweep out to a point P, and I know the areas of all these surfaces. And I can do this for any point. There's a family of curves for which I can fill in by least area surfaces. I know the areas of all of these surfaces. And moreover, if I perturb these guys, I still know for nearby perturbations, I still know what the areas of these minimal surfaces are. So this is what I mean by a manifold which admits foliations from all directions. For any point, I can do this sweep out and know all of this area information. So in this case, we're able to also show a uniqueness result. So let's suppose that the manifold admits foliations from all directions and that I know the metric on the boundary. And now here's the much larger information of data. Suppose that for any point that I have in my manifold, I can reach it by a family of curves on the boundary and fill in by all of these minimal surfaces. So if I have these curves and any perturbations of these curves nearby, I know the area of the properly embedded minimal surface that reaches this point. and it solves this least area problem for this class of boundary curves. Then from this area information, this uniquely determines the metric, and once again, up to isomorphisms, which are fixing the boundary. Okay, so where do we go from here? So in the last, say, couple minutes, let me just say some future directions that we're thinking about. Whoops. So some future projects. So one is to consider, again, this kind of anti-de Sitter conformal field theory setting that the physicists are interested in, looking at an asymptotically hyperbolic manifold, anti-de Sitter manifold, pardon me, and considering renormalized area information in this case. Another direction that we might be looking at is just larger classes of 3 manifolds. So we can do it for this 3 right now. What happens if we give ourselves more data with fewer restrictions on the manifold, or the manifold has a different structure, looking at area information in these cases and trying to recover a Riemannian metric. All right, so that concludes what I want to talk about. Thank you so much for all of your attention. And if you have any questions, I'd be happy to take them now.
Thank you very much, Tracey, for the very nice talk. Are there any questions or comments, please? Any questions or comments, please?
Okay, Tracey, this is Rakesh again.
Hello.
Hi. So I missed that part. It went a little too quickly for me. So where?
Sorry.
No, of course, you're just trying to give an outline. So where you were talking about how by taking the second derivative, you were able to get the Dirichlet-Neumann map for the slice there.
Yes.
I missed that completely. I just like how you were able to get information for different boundary functions from that. That's.
All right, let me back up a little bit.
So I mean, the reason I'm saying this is it seems like, so am I mistaken? You're saying that you have the minimal surface for this family of foliations, like this foliation.
Yes. Yep.
So that I would say is like one-dimensional data, one parameter data. Or am I mistaken there? Like the foliation for each T, there is a foliation. So
there is one foliation that I'm working with.
okay.
Okay, so think of like just one minimal surface.
Okay.
I'm allowed to perturb it up and down. And in addition to perturbing it up and down, I'm allowed to tilt it as well.
I see. So your data is not just from that foliation, but
yes,
variations of that foliation also.
But variations of that foliation also, yes.
Okay, all right, okay. And so now you took the second derivative and yeah, so I see the size here. Okay.
Yes.
Oh, okay, now, I'm missing now. What is the psi here?
Okay, so the psi here is the lapse function. So
okay.
If you want to consider the lapse function I was calling n, it's going to be the length of psi and this little n with respect to g. So psi here is telling me the push off, if you will, from each of the surfaces. So let me draw a little picture. Let's say I consider one surface here. Let's just even call this the y0 as I did in this section. Here is the unit normal to the surface.
Right.
And let's say how fast that I've moved through with this foliation. Maybe I move not so fast, so I only move a little bit up. And that would be a scaling of this normal vector field. So that would be one particular psi. But maybe I move off quite a bit. I move through this foliation, or I vary it quite quickly. So that would be another psi. So a scaling of this normal vector field.
Okay, so that's sort of like the velocity or something of the.
Yes.
Is that
so it's
okay?
like the velocity. It's telling me how fast that I sweep through this manifold.
I see. Okay.
Do I sweep through it really, really quickly, or do I sweep through it very, very slowly?
Okay. All right. Okay. Thanks.
You're welcome.
Thank you very much. Are there any other questions or comments, please?
Hi, Tracey. This is Teemu.
Hi, Teemu. How are you?
Good. I'm doing well. So just a question. So and thank you very much for this lovely talk. This was very nice to follow. So you said that one of your assumptions is that you know the boundary metric.
Yes.
So of course, in a boundary question, it's well known that you can determine the metric from the data. So did you guys think about that? And of course, now this is very different data than the boundary distance function, but could there be any possibility of getting rid of that extra assumption?
I think there probably is the possibility of getting rid of that assumption, although it's been a while since I've thought about this problem. It did pop up when we were initially thinking about this. I guess what I would need first is just how to compare the curves if I get rid of this assumption. So if I have a way of comparing the two curves and relating, or at least just mapping surface to surface in some way, then this could probably be gotten rid of. But I can't think of what mapping I was thinking of in the past.
Okay, thank you.
No problem. Thanks for that question. That's a good question.
Thank you very much. Are there any other questions or comments, please? Any other questions or comments, please? If not, thank you very much, Tracey, for the wonderful talk. Thank you very much, everyone, for coming. Thank you very much.
Thank you for everyone. Thank you for inviting me, Katya, and thank you everyone for joining.